All right, how is everybody? Ruh-roh. Me, I'm doing okay. I'm fighting weird hardware bugs, but getting the better of them eventually. But hardware is always fun compared to software because it doesn't always do the same thing twice. I had a PhD student once. He was a biochemistry PhD student, and he was getting a master's in computer science. And he told me he liked computer science because if you did the same thing twice, it always gave you the same results. And in biology, that wasn't the case. He'd set up an experiment and get one set of results. The next day, he'd run exactly the same experiment, get different results. In computer science, he felt like everything was predictable. And so it gave him, like, peace and happiness to write code and have it do the same thing every time. Which, of course, isn't always the case, right? Because sometimes you run your code 3 times and you get 3 different results. But I thought it was an interesting perspective. Mostly computers do what you tell them to. But sometimes they try to tell you what to do, like, try reinstalling your driver. But for the most part, we seem to understand what they're doing so far. All right, so I have not gotten your PA5s graded. As predicted, it's going to take a while during the week, but we'll get there eventually. Let's go. Let's get some. Oh yeah. Oh yeah, enforce updates totally. Let's look at examples of this AVL tree algorithm. And so remember our basic setup. AVL trees, they're balanced trees. And the idea is, for example, if your tree is balanced right now, when you insert a new number into your tree, it can become unbalanced. And so by looking at these balance factors on each node, you can see if your tree is unbalanced, and if it is, what you need to do to restore the balance. So let me just go through a few examples of this. And let's just build a tree. So somebody give me a number. Perfect, 12. All right, somebody give me another number. All right, do you think this tree is balanced or not? Yeah, totally. So this tree actually is balanced, and we can tell that. Let me switch to a pencil here. We can tell that by calculating the balance factor on each node. So this node, both children are null, so they have the same height. This one, left subtree height is -1, right is 0. So this has a balance factor of -1. No balance factors of 2 or -2 or bigger, so this is balanced. Yep, every BF is less than 2. All right, someone give me a third number. 47. So bigger than 12, smaller than 68. There's our 47. Let's look at our new balance factors. So this will be 0. This will be 1. This will be -2. All right. We're in a point now where our tree is unbalanced. And we know that because there's a balance factor with absolute value bigger than 1. So first thing we want to know is what case are we in? left, left, right, right, left, right, or right, left. And we can tell by just looking at this first point, right, if we insert it here, move up till you find your first spot where you have an imbalance, and look at your balance factors to see what case you're in. So we have a -2 and a right child with a balance of 1. That looks like this case. -2, right child has a balance of 1. If the right child had a balance factor of 0 or -1, then we're in a right case. But we're in this case. So we need to do a pair of adjustments. And at the, not risk, but certainty of messing up this picture, which we'll redraw later, let me just start labeling things on here. So we're looking at the right-left case. So this is going to be node, let me do this in green. This is going to be the node that's called 3. A is empty. This is going to be the node that's called 5. This is going to be the node 4. And then A, B, C, D are all null. And this says we should turn this tree into this one, where 3 is the root, the right child is 4, the right child is 5. And then A, B, C, D we don't care about because they're null. So to apply the right-left rotation, first we want to turn this tree into that. So basically we're just swapping the 5 and the 4. Right? If we had other children on here, we would have to deal with those. But basically the 47 is going to come up here, and the 68 is going to go down to the right. So our new tree should be 3, 4, 5. 3 is 12. 4 is 47. 5 is 68. And now if we calculate balance factors, which we don't need to, but if we did, this would be -1, this would be -2. That's our right case. -2, -1, 0. And again, this is 3, this is 4, this is 5. And to make it balanced, now we change 4 into the root, put 3 on the left, 5 on the right. So 4 becomes the root. So this got changed into this. And this is going to get changed into node 4 is the root, node 3, which is 12, is on the left, node 5, which is 68, is on the right. So there's a balanced tree with those 3 nodes inserted, 12, 68, 47. And it gets more interesting as your tree gets a little bigger. All right, someone give me another number. 48. Going to go to the right of this. Going to go to the left of this. Is this balanced or not? So you want to play along at home. Figure out the balance factor of each node. I'm doing this myself off screen. So what do you think, balanced or not? Yes, excellent. So this node has no children, so the balance factor is 0. This has a height of 0 and -1, so balance factor of 1. No children, balance factor of 0. Left subtree height of 0. Right subtree height of 1. This has a balance factor of -1. So that's a balanced tree. All right, give me another number. 1337. So bigger than this, 1337. So this will have a balance factor of 0. The balance factor of the parent will change because now the left and right subtrees both have the same height. But the balance factor of this node's parent is not going to change because this had a height of 0 and the right subtree had a height of 1. It still has a height of 1, so that's still -1. So we're still balanced. And when you insert a node, you can work your way up the tree to adjust balance factors, so you don't have to recalculate every single balance factor. All right, give me another number. 1738. I'm liking these numbers. All right, so this is a factor of 0. Its parent left is height of -1. This is a height of 0, so this is -1. And then this parent left subtree has a height of 0, right has a height of 2. So this is off by -2. And here left subtree has a height of 0. Right subtree has a height of 2, so this is actually a -2. But we don't really need these balance factors above here. All we care about is this first imbalance point that we discover. All right, so -2, -1, 0. What case are we in? Right, you got it. -2, -1, that's a right case. So let's label these. And we're only looking at this piece of our tree right now. Right, so the root of the tree that we're about to adjust is the first node where we had an imbalance, -2 in this case. So we're looking at this tree, and let me label these nodes. So this is node 3. This is subtree A. This is node 4. This is node 5. And subtrees B, C, D are null. And so our instructions for balancing are as follows. We should make node 4 the root. So we'll put a 1337 at the root. We'll put node 3 on the left. That's our 68. Node 5 goes on the right. That's 1738. Subtree A is the left child of node 3 still, so this is our 48. And the rest of the tree doesn't change. This is still a 47, and this is a 12. That doesn't look right to me. So that's a 3, that goes up there. Yeah, this does not look right, so what are we doing wrong here? 0, -1, 0. Oh, my bad. Let me back up a step. I did something wrong. This is why I don't have a job as a computer. So let's go back to this tree here. And we had a 12 and a 47 and a 68 and a 48 and a 1337 and a 1738. So we had just added this node and we were recalculating balance factors, and this balance factor is wrong. The left subtree has a height of 0, the right subtree has a height of 1. So this actually has a balance factor of -1. So I messed up. This is a 0. This is a -1. This is a 0. This is a -1. This is a 0. But up here at the 47, left subtree has a height of 0. Right subtree has a height of 2. This is where the imbalance occurs. All right. So it's still a -2, -1. We're still in the right case, but the adjustment's going to look a little different. So the -2 node, that's going to be node 3. So this is node 3. Its left child is A. And then to the right of 3 is node 4. And the left child of 4 is subtree B. And the right child of 4 is node 5. And the right subtree of 5 is subtree D. And so C is null, and so all I'm doing is I'm labeling the different nodes and subtrees in here based on this picture, right? Now A is just a single node, but it could be an entire subtree, and whatever, 10 million nodes you find from this point on down, that whole subtree is just called A, and it's just going to end up in this case, as a left child of node 3. So you pick up whole pieces of trees and move them around in addition to nodes. So the balanced case should do the following. We should have 4 as the root of the tree. So node 4 is our 68. That should be the root. The left subchild should be node 3. That's 47. The right subchild should be 5. That's 1337. And then the left subchild of 3 should be subtree A, so that's a 12. The right subtree of node 3 should be subtree B, so B is our 48, so that goes here. The left subtree of 5 is C, that's null. And the right subtree is D, which is 1738. So there's your balanced version after you inserted the 1738. And this, you can just tell it's balanced, right? If it had one more node here, it would be perfectly symmetric. But everything here has a nice balance factor. So this is the whole algorithm, right? Add a node and calculate the balance factors, and then if there's an imbalance, figure out which case you're in and just apply these adjustments until you get down to one of your balanced cases. Now you can try to prove that this works, that this will always leave you with a tree that's balanced, and that if you do this at the first place where you have an imbalance, the rest of the tree will be balanced. That's all stuff that has to be shown. That's something you would do in like an algorithms course, where you actually go through and prove that this leaves you with a balanced tree. We're not going to do that, but this works, right? And it's pretty efficient. And as long as you do this every time that you change the tree, your tree will remain balanced. Now, if you've added 2 nodes, it's possible you might be in a case that's not one of these, right? So you have to do this adjustment every time that you add, and you also do it when you delete. All right, questions about this? I'm not going to ask you to code this, someone else may down the road, but I might ask you to do what we've been doing here, right? Take a tree and add a node, for example. Calculate balance factors, see what case you're in, and apply these adjustments. So, so how would we code something like this? So this was my version of PA4 like code. It's not exactly PA4, I don't think. But this is like PA4, except I've added a few other functions here. There's an adjust function, which checks balance factors and performs those adjustments, and some particular subroutines called by adjust, which handle those four cases. And so balance factor is the height of the left minus the height of the right, exactly. And don't make the mistake of using the balance factor when you calculate the balance factor. It's not the balance factor difference, it's the difference in the heights of the subtrees. So I don't think we went through this code before, but this is just sample PA4 code. So prompt the user, get an input, and first thing I do is I check to see if they entered a number. So scan it with a %D and see if you got a 1 back. If you did, you know the person entered a number. And so that's an attempt to insert a number. Call your search, see if it's already in the tree. If it is, print an error message. Otherwise, go ahead and insert it into the tree. If scanf did not return a 1, they didn't put in a number, so they typed in some kind of command. So now we just switch on the first character. If it's X, that means they want to examine the root of the tree. If it's question mark, we'll give them a help message. If it's S, we're searching for something, so rescan the buffer with the format S space %D to see what number they're searching for. If it doesn't come back correctly, then they didn't put a number after S, give them an error message. Otherwise, call your search function, and if it returns something non-null, say it was found, otherwise not. Yeah, switches are cool. They're pretty powerful. D is exactly the same as S, except you call delete instead of search. But you know, rescan, see if they said D followed by a number, and so on. And this is, you know, a good example of why I ask you to do gets and then scans, right? Because we read a line from the user and we're scanning it here to see if it's a number. It's not. We're checking the first character here to see if it's an S. It is. We're scanning it again to see if it's S followed by a number, right? We're just processing this string a bunch of different ways, but that's okay because it's sitting in memory right now. If I try to do a scanf, right, every time I call scanf, it pulls my string in from the input and throws it in memory, but the next time I do scanf, that string goes away. So fget is throwing that into a memory buffer for us, and now we can look at characters in it, we can rescan it with different patterns, and so on and so forth. And then Q frees the memory and returns. Anything else gives a message to say question mark for help. So I'm not going to go through this, but I think we looked at delete code last time anyway. And insert code, right? So if it's null, make a new node. Otherwise, insert on either the left or the right. So this is not PA4. This is no license plates in here. This is just a tree of integers. So the new detail is when we add something, I call this adjust function. And I said root equal to adjust. And when we finish deleting, I said root equal to adjust. So adjust takes the root of a tree and gives you back the root of an adjusted tree. And then all of this is boilerplate code. So let's look at the adjust routine. So this calculates the balance factor of a node, right? And how does it do that? If the root is null, the balance factor is 0. Otherwise, take the height of the left subtree, subtract the height of the right subtree. That's the balance factor, right? There's almost no work for me to do here as the programmer. I basically typed in the definition of balance factor. It's the height of the left subtree minus the height of the right subtree. I already have a height function written, so I know these will give me the right thing, and I just return their difference. The only work I have to do is make sure I take care of the base case where there is no left or right subtree, i.e. the root is null. And in that case, an empty tree will just say the balance factor is 0. All right, adjusting a node, I don't think this case ever happens, but if I try to adjust a null tree, I'll just return null. Otherwise, what do we do? So, if the balance factor of the root is 2 and the balance factor of the left subtree is -1, balance factor is 2, left subtree is -1, we have to do a left-right adjustment. So what do? We say root equals left-right. If the balance factor is 2, then we do a left-left adjustment. And I'm kind of skipping some if statements in here, right? If we're in a left-right case, this will be 2, this will be -1. We'll go ahead and we'll do a left-right adjustment to come down here. If the balance factor of this is 2, there's two possibilities. Either I was in this case to start, in which case I didn't do a call to left-right and I just want to do a left-left. Or I was in this case to start, in which case I've done this adjustment and now I want to call left-left. So any time at this point that I see a balance factor of 2, I know I want to do a left-left adjustment. So that happens right here. And then here's the symmetric cases on the right. So that does the right-left, and that does the right-right, and we return the root. All right, and then using the symbology from this, which originally came from Wikipedia, but it seems to have been replaced by other pictures. But using this notion of, 5, 3, 4, A, B, C, D, here's what my left-right manipulation looks like, right? This is a balance factor of 2, this is a balance factor of -1. We want to turn this into that. Let's see. Check balance factors and do what needs to be done. Are you going to kill the root? Yeah, do whatever needs to be done. Yeah. All right, so here's my left-right code, right? It's not something you would want to try to memorize. It's not something you would want to ever try to read, right? This is code that's like write once, read never. Okay. Writing this took almost no thought, but reading it and understanding what it's doing is very complex. Okay, but how does one write this? Really, all I'm doing is exactly what we did here on paper. First, I'm labeling a set of nodes: node 5, node 3, node 4, A, B, C, D. And so node 5 is the root, right? That's just the root of the tree, the place where the tree is imbalanced. D, that's a little hard to see, is the right child of the root. So I say D equals node 5 right. Node 3 is the left child of node 5. So I say node 3 equals node 5 left. So I've set up this and this and this. I need to set up subtree A and node 4 and B and C. But I can't set A equal to node 3 left if node 3 is null. So I make all of this conditional. If node 3 is not null, then what do I want to do? I want to set A equal to node 3 left. I want to set 4 equal to node 3 right. So if N3 is not null, A is node 3 left, node 4 is node 3 right. All I'm doing is naming things. I've just got some temporary variables that are conveniently named the same as the way these things in the picture are labeled. And now I'm going to set B to be node 4 left and C to be node 4 right. So B is node 4 left, C is node 4 right. But that only makes sense if node 4 is not null. Because if node 4 is null, it has no children. If I set B to node 4 left, I'm going to segfault. So depending on what your tree looks like if there's no node 4, then node 4 should be null, B and C should be null. So to avoid doing a lot of extra if statements, I initialize all of my nodes to null to begin with. And then, if node 3 is null, I'm not going to assign, B and C, but they'll be null because I initialize them to null. So all of this is just going through my tree and setting temporary variables to point to these pieces of the tree, these 3 nodes and those 4 subtrees. And now I want to construct this tree, which looks like this. And you know what? This will probably be easier if I just keep this on the same page. All right, so how do I adjust this? I change N4 so that its left child is node 5, so its left child is equal to node 4. That's setting up this piece of my new tree. Node 5's right child is just going to be D. I don't have to change that. That's what it was before. But I need to change node 4's left and right children. But only if node 4 is not null. So if node 4 is not null, what do? N4's left child should be node 3. N4's right child should be C. So that's building this and this. And then node 3's left child will still be A, but node 3's right child should change to B, but only if node 3 is not null. So if node 3 is not null, set node 3's right child to be B. And then what do I return? The root of this new tree, which is node 5. So I return node 5. And that's the whole left-right case. The left-left case is a little simpler. So left-left, again, I'm going to name these temporary nodes. So I'll name node 5, 4, 3, A, B, C, D. So node 5 is the root, D is node 5's right child, node 4 is the root's left child, C is node 4's right child, node 3 is node 4's left child. And I'm not going to worry about A and B because A and B start off as the children of 3, they end up as the children of 3. So I don't have to worry about A and B, they're just going to get dragged along with node 3. And then the actual adjustment is simply make node 4's right child equal to node 5, right, which is right here. And node 5's left child should pick up C. So node 5 left is C, and then we return node 4 as the new root. So if you want to write something like this, right, the thought of trying to come up with this and get this just right is possibly a little terrifying, right? And I would never want to debug this. And this is one of the few cases where if I feel like I made a mistake in here, personally, I would delete and I would rewrite. Because when I wrote this, right, I really didn't want to be thinking about the logic of AVL tree rebalancing. I really just wanted to implement these cases. And if I work faithfully, right, and do each of the things that has to happen, for example, put node 4 up here, change node 4's left child to be 3, change 3's right child to be B, right, and I faithfully write code to do that, right, then I believe this code should work. And if something goes wrong, right, and I think it did a few times when I was writing this, there's no way I'm going to go back and try and edit this and patch it up, right? So this is one of a few cases where I would just rip all the wires out of the proto board and start building again. But, you know, in some sense, it's very straightforward if you know your algorithm. But this is a point that I tried to stress in PA5. You've got to understand the algorithm. Right? Once you're writing code, if you don't have an absolutely rock solid understanding of the algorithm itself, you're doing things out of order. And you should never, I won't say never, but you should almost never be writing code to do something unless you have a really, really perfect understanding of what it is you want that code to do. Good question. So someone asked, could we not make the left-right case go directly to the balanced? Yes, we could. But I wanted to do it this way. I don't remember why. But yeah, we could go directly from here to here. Yeah, nothing wrong with that. It felt like less coding for me to just change this into a left-left and then go on. Plus, I think the other reason was this was the way I was teaching it. And so that's what I wanted the code to reflect. I gave this assignment a couple of years ago to do tree balancing. But yeah, you're right, you can go directly. So that's the whole tree balancing setup. And this works. And when you insert into a tree, now this gets into one of these areas that we would have to do some work to prove. But the way it turns out, when you insert into a tree, right, if this was balanced to start and we insert the 1738, well, we check the balance factor here, right, and it's a 0. But remember, when we inserted this 1738, what we were actually doing was we were saying this node's right child equals, you know, add root comma 1738, or, you know, root right 1738. And so after we make that call, we can check the balance factor here. And that'll turn out to be, you know, still balanced. But remember, the reason that we called add to add 1738 to this tree, that was actually inside something where we were sitting at this node, and we said this node's right child equals add this subtree, comma 1738. And when we come back from that recursive call, this is the node whose right child we just modified, and we can check the balance factor here. And that still looks like it's balanced, but the reason that we were inserting 1738 into here was because in our original tree, where we got something called root, we said something like root equals add, something like root right equals add root right 1738. So the recursive nature of the add function means we're going to call add not just at this point and this point, but also when our root is equal to this. And when we come back from here, we can check the balance factor, and we'll see an imbalance, and that's going to be the first node that we encountered that's got a bad balance factor. So there's nowhere in this code where I'm starting from the node we inserted and working my way up and looking for an imbalance point, right? That's happening kind of as a consequence of the recursion. So if the tree is empty, we just make a node and it's going to be balanced. That's fine. If our data is sitting to the left of our root, we go ahead and we set the left subtree equal to insert, and then we adjust the root. And the root of our original tree may not be where the imbalance was, but this call to insert will do the same thing. It will adjust the right subtree's root, right? Something like the 68. And that's going to involve a recursive call on this subtree, 1337, right? And so this pops up and checks the balance factor. Very hard to explain in words, but the punchline is we don't explicitly have to say, okay, we just inserted this number, let's work up the tree and find the first spot where the imbalance occurs. The recursion of the add function basically walks you down to a leaf node, and when you get to the right leaf, you just tack your node on. As you unwind the recursion, which is when you come back from this recursive call, your root will successively be the next root going up the tree from that leaf node you just created. And so the first time that I find an imbalance point, that's going to be the first node where I do this adjustment. And once I've done that, the subsequent nodes will be adjusted also. All right, aren't you glad I didn't give you a PA6? But that's a fun algorithm to code and get working. There is still time. We got a few days left. I could make it due tomorrow. All right. So questions, comments about questions, comments about that. So we've got a few minutes left here. I'm gonna probably spend tomorrow and Friday doing review and things like that. But let me take a few minutes here and just mention red-black trees. And I'm pulling up a copy of the Wikipedia page on red-black trees. This is a totally different approach to dealing with imbalance in trees. And red-black trees, they're binary search trees, so they have that, less than greater than the root property between left, right. What do we call the ends of tree leaves when we are going down the roots? So the last nodes are called leaves. Why do we call the ends of the tree leaves when we are going down the roots? They're like the leaves, right? So if your tree was upside down, the leaves are the things that don't have more branches coming out of them. It's just an upside down version. So yeah, the trees we draw are actually upside down to natural trees. But then it would be a trunk, not a root. The root is like the starting point of the tree. So it's basically the trunk. Right, so here's our tree, and that's the root, and that's the leaf. Right, so just picture it upside down. Right, so that's where the tree grows from, and these branches come out, and they bifurcate and so on, and the ones that are sitting at the end with no other branches, those are the leaves. I'm not sure what trunk means, but this is basically the starting point. So that might be like, the main trunk of the tree. The terminology definitely is not perfect, but yeah. Or you can think family tree. Yeah, trunk's a more accurate term. The node trunk, there you go. So red-black trees kind of get into this because when we do the algorithms for red-black trees, we actually have to deal with things like uncles and cousins and grandparents, and that pushes this terminology a little further. But red-black trees, they're binary search trees, but they're not balanced in the classic sense. You can have, you know, a big difference in heights from one side to another, but they're balanced enough that we can say things about their performance and keep their performance in this basically log n state that we like. And red-black trees are called this because apparently when this algorithm was being developed, the person grabbed some markers and there happened to be a red one and a black one. And the name just stuck, right? If they had a green and a blue, these would be called green-blue trees. So that's why they're red-black trees. We might talk about this a little tomorrow. It's interesting just because it's so kind of strange. It does not require you to do things like, you know, rotate your tree to keep the heights similar on both sides. Oh, that would have been cool if it was from checkers. It doesn't require that kind of rebalancing, but it has what are called a set of invariants, things that must be true in the tree. And so, for example, you know, each node is colored either red or black. The root always has to be black. The leaves, the nil leaves, so here we think about the children of the leaves, right? And these are null. So those have to be black. If a node is red, both its children are black. And then here's the key property. Every path from a given node to the last nil node on that has the same number of black nodes. Right? And this is not obvious why we're doing this, but for example, if we start from the root and we go to a nil node, we have 1, 2 black nodes along the way. 1, 2, 1, 2, 1, 2, 1, 2. And that's the property that makes this tree well behaved. It puts a bounds on how gross the difference can be in height from one side to another. And it can be a significant height difference. This side could be 2 million nodes. This could be 1.5 million nodes. Right? There's no limit to how much taller one side can be than the other in terms of number of nodes. But in terms of a scale factor, one side can never be more than twice as tall as the other. And that's a good enough bounds to preserve our log n performance. And so a red-black tree describes these what we can call invariants, these 5 characteristics that always have to be true. And when we make a change to our tree, we follow that with an adjustment that tries to preserve these 5 invariants, these 5 things that have to be true. And we can show that as long as these 5 things are true, then we have this property that you know, we get a nice log n performance for searches and adds and deletes. All right, so we will leave that there. We'll either talk a little more about this tomorrow, or we'll start doing review. And if I get through PA5, we can talk about PA5 also. Cool. Have a good one. I will see you next time.